Greetings, class. I'm just joking.
All right, so the first relationship. We're going to look at the relationship between wavelength and frequency. And we kind of saw with the graphic that as wavelength increases, frequency decreases. Long wavelength, shorter frequency, right? Because, again, kind of looking over here, which you can't really see on the screen, comparing these waves, right? Longer wavelength, less frequency. Okay? And then it's opposite. As the wavelength would get smaller, the frequency would increase. It's an inverse relationship. Okay? Now, the mathematical relationship for this, okay, and men, this is a classic inverse relationship. The classic inverse relationship mathematically is x times y equals a constant. If you ever graph that, you would find that it would give you a graph kind of like this, I believe. Okay? And so, kind of an inverse graph. And so and it turns out the x is wavelength, the y is frequency, and the constant is the speed of light. It's kind of interesting. If you take the wavelength of light and you multiply it by its frequency, you get the speed of light. In a way, it kind of makes sense, though, because if you remember, the units of wavelength is in, let's say, meters, right? And the units of frequency are per second. So if you're taking, meters and you're multiplying them by per second or 1 over seconds, you're going to get a unit, because nothing cancels, of meters per second, huh? And it turns out the speed that's going to turn out to be is the speed of light. Okay, I'm going to scroll down and we're going to look at a sample problem based on this equation. So a photon of microwaves has a wavelength of 3.2 times 10 to the negative second meter. Actually, that's 3.2 centimeters, if you think about it, yes? What is the frequency of that microwave? And so if you have this equation where you have a relationship between wavelength and frequency, if you know the wavelength, and when I look at a problem like this, it says it has a wavelength of blah, I put a little lambda next to it because that's my wavelength. And what I want to know is the frequency. You with me? And so then what I'm going to say is, well, I need to know the equation that has wavelength and frequency in it. And gentlemen, there's going to be 3 equations here that we're going to be using for the 3 relationships. So it's going to be important when you look at a sample problem like this, or a problem, that you identify which equation you're going to need. Right now we only know 1 of the 3 equations, but eventually there's going to be 3. So I call this diagnosing the problem. In other words, what kind of problem is it? This is a wavelength frequency problem. So I need the equation that includes wavelength and frequency, lambda and nu. You with me? Okay. And so what I like to do, I always like to solve for the variable that I'm asking for, and then I plug in the numbers. And because there's a lot of units here, I'm going to use the factor label method to set this up. Again, factor label method, very good for solving problems where there are units. So let me set this up. Okay. So I'm going to draw my thing. I have a photon, and so I solve photon with this wavelength. I solve it, and I need to take the speed of light and divide it by the wavelength. So the speed of light, we're going to use 3.00 times 10 to the 8th meters per second. And remember, whenever you say per, you're crossing the line. You remember that horizontal line is like the separation between numerator and denominator. And then lambda is 3.2 times 10 to the negative second meters. Now here the wavelength is in meters, and when I want to hit equal, and I'm going to get out my calculator here in a sec, what I'm going to do is I'm going to cancel the units. Meters cancels, And the answer I'm going to get is going to be in inverse seconds, right? The answer is going to be per second times 1 over seconds, or per second, right? And that's good because that is the units for frequency. So I take this number, the speed of light, and I divide it by 3.2 times 10 to the negative second, and I get a very, very large number. And it turns out that it's, I have to figure it out. I'm going to write it down here just for 9375 and then 6 zeros, right? And for some reason, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer would be 9.375 times 10 to the 9th per second. Okay, you can just say per second. Oh, darn it. 9.375 times 10 to the 9th per second. That means waves per second. And actually, there would only be 2 sig figs in this answer. And so I would say 9.4 times 10 to the 9th waves per second. So that's that microwave. Next sample problem. A beam of electromagnetic radiation has a frequency of 5.21 times 10 to the 15th per second. What is its wavelength? So this is kind of the opposite question. Here, I know the frequency, and I want you to find the wavelength. Again, then I need the equation that has wavelength and frequency in it, and I want to solve for wavelength. When I do that, I find that lambda is c over nu. So let's use the information in our problem and write this out. So the speed of light, 3.00 times 10 to the 8th meters per second. And I'm going to divide that by 5.21 times 10 to the 15th. And when I say per second, remember that's in the double denominator, so seconds gets kicked up into the numerator. And now let's look at our units. Did we set this up correctly? Well, seconds are going to cancel. My answer is going to be in meters. Isn't that what you want for wavelength? Wavelength should be a length unit. Okay? And so, does anybody have the numerical answer for me with their calculator? Nice and loud. Anybody? Hopefully, in your calculator, you found that this is and I'm going to just round to the 3 sig figs now, 5.76 times 10 to the negative 8th meters. Now, when you get a small number like this, often I may ask you to convert this to nanometers or convert it to micrometers or something like that so that you would have a sensible number instead of a number times 10 to the negative 8th, right? But for this one, I didn't specify the unit of wavelength, so you can leave it like this. All right, let's look at the second relationship, which is going to be the relationship between energy and frequency. I just called it the second relationship. It could be the third relationship, but I'm just calling it the second one. All right, when we looked at the graphic, and we kind of really quickly looked at it again today, we saw that as frequency increased, the energy increased, right? Because radio waves had a small frequency and they have low energy. Gamma rays have a very high frequency, trillions and trillions of waves per second, right? And they have a very high energy. Remember I said, gamma rays in a high enough dose could vaporize you, right? That's crazy how much energy they contain. Billions and billions times more energy, trillions of times more energy than radio waves. Okay, anyway, so that means that energy is directly proportional to frequency. And it turns out that, and this is what Max Planck did. remember we had, Max Planck, who was in the atomic model series. He was somewhere in around 1900, 1905, and he figured out about this relationship between energy, frequency, and wavelength of light. Well, if you plot the energy contained in a beam of light versus its frequency, you get a straight line relationship. That's your easiest direct relationship, that's directly proportional, right? Okay, if you plot the frequency, so this beam of light here has this frequency. This beam has this frequency. This frequency has this energy. This frequency has this energy. This frequency has this energy. Oh, and the next higher frequency has this energy. And what you find out is that it is a straight line relationship. I didn't make that line very well, but you get the idea. Okay? So that means that as frequency increases, energy increases. And gentlemen, it's just as important to know the relationship as it is to know the mathematical equation. Okay, you should know this relationship, and then the equation is just a manifestation of that relationship. And when you have a direct relationship and you get a plot like this, you know that it is a straight line. And so that would mean that in that case, think about this. The energy in the light is going to be the slope of this line times the frequency, isn't it? And there's no y-intercept. If you don't have any frequency, you don't have any energy. The y-intercept is 0, right? If you have no frequency, no light, you have no energy. So it really is the origin if you had no frequency. So the straight line relationship here, again, I didn't draw that line very well, right? I wonder if yeah, there you go. That's a little better. Still not great. It's not going through the origin, but it turns out the slope of this line is a constant, right? And so the mathematical relationship, this is like y equals mx, right? And m, the slope, they gave the name Planck's constant. Why? Because Max Planck figured all this stuff out. Okay? And it turned out and for some reason, I'm not sure why, but they gave it the symbol H. I have no idea. He was German. Maybe H is the first letter of whatever word they were trying to describe with this slope. I don't know. A lot of times that happens. That, the original work was done in German, and so the name they gave to it was German, and the first letter of that word was H, or whatever, some letter that wouldn't be the first letter of the English word. Well, we got to go with it. It was called H. And so one of the most famous equations in science, almost as big as E equals mc squared, and F equals ma, force equals mass times acceleration, those are physics ones, is energy is H nu. Okay? So E equals H nu says that energy is some constant that they call Planck's constant. And all it is, men, is the proportionality constant between these two measures, frequency and energy. Unfortunately, it has an ungodly unit of joules times seconds. If you recall, joules is the unit of energy. And I don't know what a joules second is. I know what a meter per second is, right? It's a speed. I don't know what a joule second is, but you know what? That's just the units of the constant. We got to go with it, okay? And so now we're going to scroll down here in a sec, and we are going to go over a sample problem. Okay, so here's our sample problem. What is the energy of a wave with frequency of 5.21 times 10 to the 15th per second? And that's how you would say it. So again, I'm looking at this. Energy is E. Frequency is nu. So, I need the equation that has energy and frequency in it. That's the second equation. I'm not going to use the first equation. That has lambda in it. That ain't going to get me nowhere, is it? Not with this problem. So I'm diagnosing the problem. What is the energy of a wave with this frequency? And this is the equation. And then all you have to do now, it's already solved for energy. You don't have to resolve. You don't have to rearrange it. You just plug in the numbers. And so, what's H? H is 6.626 times 10 to the negative 34th joules times seconds. And because there's units, guess what? Factor label method. And then nu, 5.21 times 10 to the 15th per second. Now, if you're calculating energy, aren't you expecting to get joules as your answer? And I know I set this up correctly then because look, seconds cancels. And my answer is going to be in joules. Okay? And when I multiply these together, I get 3.45 times 10 to the negative 18th joules. Now think about that. That is an incredibly small number, right? So this one single beam of this light has an energy of right? And that's an incredibly small amount. What that says is individual single beams of light don't contain a lot of energy. Even a single gamma ray, it contains a lot more energy than this, as we will find when you do the worksheet, because I have you do a calculation on gamma rays and their energy. But add it up together. Are you ever hit by one beam of light? Heck no. That light bulb up there is emitting billions and billions of beams in any 1 minute. So the energy does add up, okay? Each individual beam is small, but multiply this by, a couple of trillions, right? Or a trillion beams hitting you per second, or, hitting you. It's going to be a significant amount of energy. It could be, okay? Okay, the third relationship is that between energy and wavelength. We kind of saw. Big wavelength has small energy. Think radio waves. Small wavelength has a larger energy. We said that gamma rays have the smallest wavelength and they have an incredible amount of energy. So it is an inverse relationship. Now, we don't have we will eventually have a single mathematical relationship, but to get it for wavelength, we have to combine the two equations that we already know. Okay? If we know that wavelength times frequency is the speed of light, what I can do, I'm going to do the little derivation here of how we're going to get this equation for the relationship. What is the mathematical relationship then between wavelength and energy? What I'm going to say, I'm going to solve this for frequency. And then what I'm going to do is I'm going to substitute that frequency in the energy equation, because I need to introduce energy. I'm going to replace that with C over lambda. Got it? You with me on that? You see that? That's all I'm doing. I'm solving the first equation that we learned for frequency. And then essentially what I'm doing is I'm taking this not sure why it's not letting me select that. Oh, okay. Now it's not going to work. I'm going to replace wherever I see new. In this case I'm going to have to erase this. Okay, and then what I'm going to write over there is C over lambda. Normally I just kind of select that and drag it over so you can see. Doesn't that make sense? Wherever I see new, I can replace it with C over lambda. And so we get the equation ends up being that energy is equal to Planck's constant times the speed of light divided by the wavelength. You guys see what I just did? All I did was solve this for frequency. And then I took frequency here and I did a direct substitution of C over lambda for nu over here. Okay? And so now I have the equation energy equals Planck's constant times the speed of light divided by the wavelength. That is the third equation. You don't really even have to memorize the third equation if you don't want. I recommend it though. It's kind of not hard to memorize it. You could always derive it over and over again based on the first two equations that we learned. But sometimes it's just easier to memorize all three rather than have to do the algebra for this. Okay? So now we're going to look at a sample problem. So the last sample problem here is an energy wavelength problem. What is the energy of a photon? It's another name for one single beam of light is a photon of electromagnetic radiation with a wavelength of 3.49 millimeters. And I'm highlighting millimeters there because there's something that we need to realize about wavelength. When you're given the wavelength and you're not given the wavelength in meters, we're going to have to do something to that unit, and that something is convert it to meters. But we're going to do it inside the problem solution using the factor label method, okay? Now, 3.49 millimeters, that's probably going to be a microwave, I think, or somewhere between microwave and infrared, I would guess, okay? And so let's set this up. Well, all right, let's do the diagnosis. What is the energy of a photon with a wavelength of that? Oh, I need the equation that has energy and wavelength in it. Oh, that's the third equation that Mr. S told us about. Okay? See how I'm diagnosing the problem? And I realize that, oh, I want energy and wavelength. I want energy, I'm given wavelength. I need that third relationship. Okay? Also, you may notice before we plug any numbers in here, isn't that an inverse relationship? As the wavelength would get bigger, wouldn't the energy go down? See? Makes sense. All right. Let's plug in the numbers. Now this is going to kind of be ungodly with these crazy numbers, but 6.626 times 10 to the negative 34th joules times seconds. The speed of light, we're going to use 3.00 times 10 to the 8th meters per second. And now we just have to divide by the wavelength, 3.49 millimeters. And then let's look at the units like we typically do. Seconds cancels. Oh man, meters doesn't cancel. Well, why doesn't meters cancel? Because this is in millimeters. And so what I can do though, you know your metric mnemonic, you know milli, right? You know that there are 1 times 10 to the third or 1,000 millimeters in 1 meter. The reason I set it up that way, that conversion factor, because I want meters to cancel and I want millimeters to cancel. Because I just want to be left with joules. You see what I just did there? Now, if you don't like doing it that way, you can convert the wavelength to meters first. But gentlemen, the reason you always have to convert the wavelength to meters when you're plugging it into one of these equations is the speed of light always comes in meters per second. Got it? And whenever the speed of light is in the same equation as wavelength, like it is in the first equation and the last equation, right? Lambda times nu is c, or E equals h times c over lambda. If the wavelength is not in meters, you have to convert it to meters because whenever you plug in, I'll say it again, the speed of light is always in meters per second. Now, could you convert the speed of light to millimeters per second? Knock yourself out. You could do that instead of converting the wavelength, right? But either way, the units for the speed of light and the units for the wavelength have to be the same, otherwise they're not going to cancel out. Got it? Because they have to cancel out because you need joules. Okay, I'm going to pause the video here and we're going to get the mathematical answer. And when I plug it into the calculator, I get that the energy is, and I think I'll round to the 3 sig figs, 5.70, that's rounded, times 10 to the negative 23rd joules. Now I said this was like a microwave, right? Or it might be infrared. It's kind of on the borderline. I think it's probably a microwave, okay? Now that is times 10 to the negative 23rd. Gentlemen, so I said this is kind of, what was that? What was the energy of that other beam of light? Read me off the answer to the last problem where I gave you the frequency. Anybody have that number? It's times 10 to the negative 18th. Go ahead.
3.45 e to the negative 18th.
Negative 18th joules. Okay, now I'm here to tell you that this energy times 10 to the negative 18th is probably going to be ultraviolet light. And I know that because I know what the powers of 10 are in my brain after doing this for 20 years, right? What the power of 10 in the energy tells you what band of the spectrum it is. Visible light is usually 10 to the negative 19th. And so 10 to the negative 18th is more energetic than visible, so it's probably UV, okay? Gamma rays can be even as high as 10 to the negative 11th. And radio waves and microwaves, radio waves can be 10 to the negative 25th because they're the lowest energy. So in other words, looking at the energies, I don't expect you guys to know this by now, but if you keep in the back of your brain, though, that visible light is right around some number times 10 to the negative 19th joules, that's just kind of a handy thing to have in your gourd, right? When you're trying to, like, when you're working on these things, and does this energy value make sense? Okay, you kind of with me? If you know that I say, oh, you have a radio wave, what is its energy, right? A radio wave with this wavelength, what's its energy? And you get a bigger number, a number bigger than 10 to the negative 19th, then you know you did something wrong, right? Because 10 to the negative 19th is visible light, and it's kind of right in the center of the energies, right? So there are going to be energies with much less powers of 10, all the way down to 10 to the negative 25th, radio wave, or even up to 10 to the negative 11th gamma rays. Okay? So again, you see that these powers of 10 are important here because the span of energy is enormous, right? The span of wavelength is enormous. Remember we said it can go from football fields to, 10 to the negative 20th meters or something like that. Okay? So this is the way it is. All right, so I'm going to pause this now.